Okay, now bile synthesis part 2. The next major component in bile are phospholipids. Now the structure of phospholipids is also conducive to proper fat emulsification because we also have an amphipathic structure. So recall the structure of a phospholipid. We have a glycerol backbone, simple 3-carbon backbone, and then conjugated to this is where we have our fatty acids. And these are our long hydrocarbon tails. We have them both in the number 1 and 2 position. And these fatty acid tails have long CH2 groups, hydrocarbon, giving it a very hydrophobic property. And then on the end carbon, we have what's called a head group. And recall this head group is a phosphate. And then we can have a charged or neutral moiety on here. The most predominant phospholipid in bile is phosphatidylcholine. Which will take on this structure. Phosphatidylcholine is essentially a tertiary amine which has a permanent positive charge to it. This region of the molecule, of course, is hydrophilic. And again, combining these two features, we have an amphipathic molecule. Now, why is amphipathic molecules, why are they so important in lipid solubilization? Well, the principle of this is the same as in using detergents in your laundry. Proper detergents need to be able to lift grease and fat spots off of clothes. So in order to do that, we need a molecule that has solubility properties that are compatible with a fat. That would be the hydrophobic domain. But we also need portions that are compatible with the aqueous environment. Same situation in our gut. As we eat that delicious hamburger that is loaded with fat, part of what we're going to be ingesting are called lipid droplets. And these are large dietary lipid droplets that need to be processed in digestion. And we'll see the enzymes that are involved in digestion. But these enzymes that need to process this need to remove the fats from these lipid droplets in order for the body to absorb these fats. So we are going to be processing these things, these structures, into fatty acids. Now, what we need to consider is the surface area, surface to volume ratios. This is a very, very small surface to volume ratio because we have a large volume and the surface around it. These enzymes have to attack this in order to generate these fatty acids. What is more efficient than this is if we take these lipid droplets and we undergo the process of emulsification. Now, emulsification is not breaking covalent bonds. It is just disrupting the fat. And it is this point right here is where our bile salts plus phospholipids have their greatest effect. The process is called emulsification. Now, what is emulsification? Very simple. If we have an amphipathic molecule, the hydrophobic portion is going to enter the lipid droplet. The hydrophilic portion, which would essentially be a charge group or something that is polar interacting with water, will remain on the surface. If you have enough of these hydrophobic domains, you are going to have enough of these inserted into the large lipid droplet to essentially carve off a piece of this lipid droplet and form a smaller droplet. Now we have a much greater surface to volume ratio here, so we have more surface area for the enzymes to work, and that is going to essentially increase efficiency of digestion of fats. And that is the purpose of the bile salts and the phospholipids. Now the other component of bile are the bile pigments. Bile pigments are going to start out as digestion products from red blood cells. Now recall, this structure is the heme structure. We have 4 Pearl rings. We'll look at this more in hemoglobin metabolism. But we have the hemoglobin, the heme structure in the hemoglobin, and we have iron at the center, which is coordinated by these nitrogens here. So this is our heme structure. Now, when red blood cells, of course, are marked for degradation after their lifespan, they enter the spleen, and splenic macrophages are going to degrade the red blood cell and recycle those products, and also it's going to degrade the heme inside the red blood cells. So the process first is that we have to extract the heme from the hemoglobin. The hemoglobin will then be digested by proteases in the macrophage. And in order to degrade the heme, the first thing we're going to do is remove the iron. The iron, of course, is recycled and used for new red blood cell synthesis. The heme, however, must be degraded. After the iron is removed, we have our enzyme called heme oxygenase that is going to break open the heme ring structure. And in doing so, being an oxygenase, we are going to use oxygen as the catalyst for this reaction, putting oxygen into the group, and then we are going to essentially break off this structure, and it will be degraded. Pardon my drawing here, it'll get better as we go on. Once this is opened up, our oxygens are here on the end. This is called bilirubin. Bilirubin is then excreted from the macrophages, secreted into the bloodstream, and the bilirubin will then travel to the liver. The liver takes up the bilirubin structure, and in order to be able to get rid of the bilirubin, we need to prepare this molecule so that we can increase its solubility. So the liver does this by adding a glucuronic acid moiety. Now, glucuronic acid is a long carbon chain with lots of hydroxyl groups on it, a carboxylic acid at the end. The important thing to remember this is that we are increasing polarity. Now recall from general chemistry, as we increase polarity, we increase solubility in an aqueous environment. So we are going to put 2 of these groups on the bilirubin, and this is going to be bilirubin diglucuronide. This, in medical terms, is considered conjugated bilirubin. This original is unconjugated. So unconjugated bilirubin is bilirubin that has not entered the liver hepatocyte for this conjugation with glucuronic acids. After the liver processes it, makes conjugated bilirubin, this is then placed into the bile for final exit into the intestine. And it is this color, this is what gives the bile color, because it's a pigment and we have lots of resonance around these rings.